It's a common mistake that advanced modeling makes testing and experimentation unnecessary in engineering and science. In fact, it's the opposite. More advanced models require more advanced testing and experimentation to verify the predictions of the models. In testing, for instance, carrying capacity of an existing bridge, you need to know the state of the material, any deterioration process. Then you need to see how that material behaves in the actual structure.
With the wind turbines, I always said that you learn 20% from the test results in the test report, and you learn 80% from being able to design the test, to witness the test, to validate the test measurements, etc.
It's been an ambition for a long time at the Technical University of Denmark to establish a center that covers a wide range of scales, from the sub-micron scale up to full-scale monitoring and experimentation.
DTU has been one of the leading research facilities within wind for the last couple of decades. This new facility gives us the opportunity to get the last 80% of the learning and to combine those learning into a bigger picture.
With the establishment of CASMaT, the Villum Center for Advanced Structural Materials Testing, we have established 3 lab units: the Materials Testing Lab, the Structural Lab, and the large-scale facility.
In the materials testing lab, we have a servo hydraulic testing machine, so we can do testing from big specimens from about 1 meter size down to smaller size inside a scanning infrared microscope. And we can test at the X-ray tomography, where we can rotate specimen and see inside materials in 3 dimensions.
The structure lab works on a number of length scales ranging from material testing on smaller coupon specimens all the way up through substructural tests and full structural tests that we test on the strong floor.
The large-scale facility, that's where we test the full complexity of the structure with the interaction of the different parts. We really understand how it was designed and what the real fracture or failure mechanisms in the structure are.
We decided early on to demonstrate the capabilities of CASMaT as a multi-scale facility by starting an internally funded research project, studying fatigue in wind turbine blades, looking at the generic aspects of fatigue mechanisms and the way that fatigue mechanisms interact at various scales.
Composite structures have been studied in terms of fatigue loading for decades. But the micromechanical mechanisms are not included in the kind of fatigue laws which is used in industry at the moment.
The overall hypothesis is that fatigue is something that starts on microscale, and we can develop models of structural failures of big structures. But it also needs to be tested out with experiments, and that's what CASMaT is all about.
To do that, we have started 3 PhD studies, each working on their individual scale, but in a very integrated manner.
The purpose of PhD 1 is to study fatigue damage from its initiation at microscale and its growth up to kind of macro scales.
Whenever a failure occurs in a structure, it is because of the many local failures. So one has to understand these local failures in order to precisely estimate the failure. Based on the data we obtain from experimental investigations, X-ray computed tomography and scanning electron microscopy, we generate a numerical model, and then we propose an experimental framework that allows the prediction for fatigue based on the crack propagation phenomena.
PhD 2 covers the macromechanical model development, using input from PhD 1 in terms of knowledge about the micromechanical mechanisms which happens during fatigue loading.
The main focus of my PhD study is to basically develop in-plane fatigue damage laws due to biaxial loading at the macro scale. Carrying out experiments with the biaxial testing machine, the biaxial law that will be developed is expected to predict fatigue failure in composite laminates. The findings will be validated at 2 levels. The very first level is the macro level in the biaxial testing machine. The second level would be at the structural level, which will happen in close collaboration with the PhD study 3.
The focus with the PhD 3 is to look at full scale, but also to develop methods where you can make smaller models to predict what's going on at full scale.
We're using a numerical model to calculate the loads that go into our experiment. And then from that experiment, we return the reaction from the experiment into our numerical model. And we do that over and over again. It's an iterative loop of trying at the full structure, seeing if it works, and then sending the results back to PhD 2, PhD 1, and see where we can improve. At the end of the study, we plan to have a fatigue model that can determine the fatigue life of a structure.
This will be the first project that kind of pioneers a new way of doing really close linked experiments on length scale. And it's something that is really the heart of the CASMaT project.
Many people do this type of research, but it's rare that you see the whole range from microscale to full scale put in action, so to speak, in one project.
In order to continue within the industry to build turbines bigger, more cost efficient, more reliable, we need to understand our materials and our components better. And this new center definitely enables us to, in the future, continue that development.
The CASMaT Center and its capabilities will shed light on the possibilities of doing much more refined and intelligent testing to develop our structures and materials.